We're now ready to discuss the second part of our lesson that introduces completion stage methods in the Java Completable Futures framework. We're going to talk now about how the methods that are part of Completable Futures completion stage portion of Completable Futures help to avoid blocking and why that's important. So when you use completion stages, one of the motivations for doing so is to avoid and/or minimize blocking the calling thread. Now, if you recall when we talked about the basic completable future features, and even when we talked about the factory methods, the examples I'd shown all had a call to join, waiting for that asynchronous computation to complete. And I complained and said, that's kind of superfluous. It impedes different things. It slows stuff down. It chews up threads, and so on and so forth. So we're going to focus a little bit in more detail about why that's a problem and why completion stages are the solution to that problem. So in general, as a rule of thumb, you should avoid calling join or get until you absolutely have to. And in fact, when you do your programming assignment number 3, I think I say somewhere that only call join in this one place. There's one place where join gets called. Nothing else should use join. And you'll find yourself occasionally when you do the program wishing you could call join, because it would make your life so much easier because you wouldn't have to figure out completion stage methods. But resist that temptation, because you'll get marked off or you'll lose points or the unit test will complain at you because you're only supposed to call join in one place. Why do we not want to call join? What's the motivation for that? Well, by not calling join and by not blocking the caller, we can make the system more responsive. And remember, the purpose of responsiveness is to avoid this awkward situation where a calling thread performs an operation that runs for a while, and that calling thread is the user interface thread, and therefore the system becomes not responsive because it's waiting for the result to return and unable to be canceled or changed to do something else or do some other kind of completely unrelated operation that would not interfere with the longer running computation. And if you recall, the older systems like the Mac or Windows will give you funny icons like an hourglass or a spinning color wheel that indicates things are taking too long to run. On Android, you'll get an application not responding exception. So aside from the fact that it's just annoying to not be responsive, blocking also has performance implications. It impedes inherent parallelism. You don't take as much advantage of the underlying processor cores as you could. It also conceivably can complicate program structure because the ways around blocking historically before completable futures have largely involved using single-threaded event programming models, which are just ugly and hard to program. So we really don't want this thing where we have two-way calls from the caller thread to the callee, and the caller has to block until all these calls are done. We'd like things to be able to run concurrently. Another reason, of course, is that by doing it this way, you're at the mercy of whichever calls take the longest to run before you get results. So if it turns out that you make 3 calls and the first one takes a long time, but the other 2 take very short time, by forcing things into the Procrustean bed of two-way calling models, you wait until the first one is done before getting any results, whereas if you ran these asynchronously, the ones that took less time to run would already have returned, so you could do something with those results while you're waiting for the longer running result to return. Now, clients can often avoid blocking generally until a result must be obtained. And of course, there's situations where you absolutely have to get a result. So if you're doing some kind of user interface programming, you eventually want to be able to print a result. And so if you can no longer make any progress in your computation, then your client may have to wait. Sometimes you can get around that, and that's why we have things like RX Android, which works very well in environments like user interfaces on mobile devices, where you really don't want to block, you just want to be called back when things are done. So sometimes you have to wait, but oftentimes you don't. For servers, in contrast, it's almost always the case that you can avoid blocking altogether. Clients often have to finally wait for something so it can display a result to the user under various circumstances. But servers typically are in this wonderful situation where a result comes in, you can go ahead and have a single thread take the result from the network interface and then delegate it to some pool of threads, and then non-blocking operations take place so that you keep everything humming along and there's no threads that are ever blocked waiting on anything. And then when the result is finally processed by the server, it can return the result back to the client as a reply or as a response from whatever context the server happens to be in. So it may be the case the server never has to block at all. So that's kind of the ideal situation. So often clients don't have to block. Usually servers don't have to block. So you can basically use completion stage methods to chain together async result processing. And I like to think of this with a juggling metaphor. Anybody here who's a juggler, the whole purpose of juggling is to try to keep as many balls in the air as you can and only hold them synchronously in your hands long enough to either throw them back up or switch hands and throw them back up. So the goal is to be able to have more things in the air than you have hands. So in this particular context, the balls in the air correspond to asynchronous computations, and your hands correspond to the relatively brief period of blocking when you grab something and then shift to another hand and then throw it back up again, or however you might want to juggle. So that's a good metaphor to think about when you think about programming asynchronous models and completion stage methods. They allow you to keep more balls in the air, which is good because the longer things block, the more it impedes performance. So the basic motivation here in the context of Java completion stage methods is you only consume resources when an action is running, which reduces system overhead. And that's why when we've looked at some examples earlier, we've seen that the CompletableFuture versions often run better than the parallel streams versions. Okay, so that is the end of the discussion about introducing completion stage methods. We'll come back and talk in more detail about those methods here starting in just a moment.